Hello and welcome to Little Big Physics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we asked ourselves if we could predict what would happen when two blocks collided. It seems like we might have run into something of a problem with the setup of that experiment, however, and we've determined that whether our model is really correct hinges on a simple question. Do you really have to push harder to make a heavier object move as fast as you would a lighter one? Intuitively, the answer would seem to be yes, but can we really prove that it's true? That's what we're going to try to do today. It actually turns out to be a bit more challenging than expected. Is there a good way to produce the exact same push on two different objects, for instance? If we can give two objects, one heavier than the other, the same shove, and the heavier one moves more slowly, that would suggest that you really do have to push harder to make a heavier object move as quickly. Our best bet would probably be rockets, but it's hard to trust them, since we actually haven't quite figured out how they work yet. Recall that a rocket at 0% thrust will actually still push a block, for instance. Our dear friend Sackboy could be of assistance, but would the blocks scraping along the ground as Sackboy pulls them cause any unexpected problems? I think we're looking at this the wrong way. Instead of taking two blocks, applying the same push to them, and then seeing how they move, why don't we make both blocks move the same way and then measure the push that it takes to do that? Then, if the heavier block needs a stronger push to speed up as much as the lighter block does, that means the assumption we made last episode was correct. How can we do that, you might ask? What have we seen that makes everything, no matter what it is, move in the same way? At least for a moment. Think back to our air resistance episode. Even though we know that two objects of different weights will fall slightly differently, we saw that for the first few moments, a light object and a heavier object will fall side by side if you drop them. This seems to suggest that, at least at the very beginning of the fall, there's a downwards push that's just strong enough on each respective object to make them move exactly the same way. Do we have any way of measuring how strong this push is, then? Luckily enough, we've actually already found one. Remember our scale that we made a long while back? We know that it shows us how heavy something is, but let's remember exactly how it works. When we lay an object on the scale's platform, gravity pushes down on the object, and that pushes down the platform in turn. The distance that the spring extends is directly proportional to the heaviness of the objects on the platform, as we found when we doubled the blocks on the platform and saw the spring stretch twice as far afterwards. The reading on the screen is actually how far the spring has been stretched from its original position. In real life, spring scales work just like this. There's another variable that we can change too, though. If we attach an anti-gravity modifier to the block on the scale, we can also change the strength of gravity itself. Conveniently, setting one block to 10% gravity and another to 20% gravity results in the latter being pushed down twice as hard as the former. This confirms that pulling a block down faster, like stronger gravity does, corresponds to pulling it harder. It seems obvious, but it's good to confirm. It also means that we can use gravity instead of rockets to reliably apply a push of a known magnitude to an object, since rockets had some issues when we tried to use them. By using the anti-gravity modifier, we can subject the same object to various pushes of a known magnitude. Through a combination of the modifier and changing the heaviness of the object, we can subject different objects of different weights to a push of the same magnitude, as you can see here, with one block experiencing the same downwards push as two blocks experiencing gravity of half the strength. Let's get back to what we originally wanted to test, though. Did you notice how the downwards push on the left scale doubled when we doubled the heaviness of the block resting on it? Since we know that both the original block and the doubled block move the same way as a result of this push, we can see that a block of twice the heaviness must be pushed twice as hard to move in the same way. That means that yes, heavier objects do need a harder push to move as quickly as lighter objects, which gives some credit to our explanation for why some trials in the last episode had unexpected results. We probably should still test that episode's equation a bit more, though. I want to try to explore the implications of this discovery some more, too. we've seen the following relationship between heaviness, the strength of a push, and how quickly something moves. Here, A is how quickly the object moves. It's not speed exactly, because what's actually happening is that the object's speed is changing. We'll call the change in an object's speed its acceleration. Acceleration can be measured in speed units over time, like lengths per second, which you might just call lengths per second squared. For example, an object with an initial speed of 0 lengths per second and a constant acceleration of 2 lengths per second squared would be moving at 0 lengths per second at first, 2 lengths per second a second later, 10 lengths per second 5 seconds later, and so on. F is how strong the push is. We'll talk about that more in a moment. M, like usual, is just the heaviness of the object. This equation tells us that if we want two objects of different heaviness to accelerate at the same rate, we need to push the heavier one harder than the lighter one to achieve that. For instance, like we saw earlier, you need to push twice as strong for an object that's twice as heavy. If you double both F and M, A stays the same. Let's take a closer look at F, though. What units do we measure the strength of a push in? If we just rearrange the equation like this, we can find out. This tells us that the strength of a push is defined in units of heaviness times acceleration. For example, mass lengths per second squared. That's really a mouthful, so let's give mass lengths per second squared an easier name, as a shorthand. Since it's how hard we're pushing something, we can call this quantity force. Our usual mechanism of adding an S for sac won't really work, so let's call this unit the Stanford, for standard force. What's kind of awkward right now is that we're yet to actually determine just how strong the Stanford is, so it's really just a name to us. Let's see if we can correct that. It seems like it might be tough to determine the strength of one Stanford directly, at least using gravity. Here's an idea though. If we look at the equation F equals ma again, we see that we can determine the force of gravity indirectly by multiplying the heaviness of a falling block by the downwards acceleration of that block. We have the impression that gravity makes everything accelerate at the same rate though, so we do have some leeway. All we have to do is find out what that one acceleration is, and then, if we multiply it by the right heaviness in masses, we'll have a force of 1 Stanford. Do you remember back in the air resistance episode, when we made a massive metal block and measured its position as it fell? I've transferred its graph into Excel, and I've produced a fit for the first 2 seconds of its descent. I didn't account for the entire time it was in the air, since then air resistance would have too much of an effect. The fit still isn't quite perfect, so this is really an approximation, but if I got rid of any more data points, I'd be worried about any error for each individual point having too much of an effect on the result. The fit had the stipulation that its peak has to be at time equals 0, since the measuring started right as the block began falling. We get an acceleration of 66 lengths per second squared, but keep in mind that this is just a tentative number. Since our fit still doesn't seem quite perfect, this is just a rough estimate of how quickly gravity makes things accelerate. We might want to work on this some more in the future, but unfortunately, I'm not really sure right now what we could do to prevent air resistance from souring our results. It might take a more math-heavy approach. Anyways, if the acceleration is 66 lengths per second squared, the equation tells us that gravity produces a downwards push of 1 Stanford on an object of heaviness 1 over 66 masses, or about 0.015 masses. 1 Stanford, then, really isn't all that much, since it's only enough to pull down an object less than 1/60th sackboy's heaviness at free fall speeds. An object of 1 mass, on the other hand, would experience a downwards push of around 66 Stanfords. Of course, we'll hopefully have a more specific number someday in the future. I feel like we've really learned a lot today, and it's going to take us a long time to exhaust all of the new avenues of exploration that have opened up. For one, it's looking like our explanation for the results we got in the last episode is correct, which means we can now look further into the idea of momentum. Having a basic understanding of this notion of force and how it relates to movement also grants us access to an entire world of objects interacting with each other in ways that we hadn't been able to model before. Our deepened understanding of gravity is one example, and I already have plenty of ideas of how we could study it even further. For now, though, I think we've done enough for one day. I'll see you all later when we embark on yet another journey to learn about the world of Little Big Planet, increasing our understanding bit by bit. Until next time, and stay curious.